Okay, I think that we're live. Checking all my stats here. Everything looks good. And good morning, and live from Santa Barbara, Winter Hall, it is CS-030. Hey! I haven't got my applause track yet, but that's coming. We are in Santa Barbara. This is Westmont College, and we are in Winter Hall. We're broadcasting CS-030, which is our second programming class here at Westmont. This is a Mayterm seminar, part of a 5-week class. Today's lecture is scheduled for 2 hours. We're going to be moving between decision-making and loops today. We are communicating real-time on Slack for those people that are within Westmont's firewall. I guess anyone that's in the Slack channel is able to communicate on that. And that's at #broadcastquestions. We've got a live studio audience here today, and we've got several people participating from abroad. So shout out to Flo and James and Amy and Nicholas and Boaz and Tim, who are certainly watching us remotely today. So great. As we do every day, let's just take a minute to set ourselves up for success. Got to make sure my notifications are off everywhere, and whatever we don't want to be monitoring, have that off. Check over here. I think I'm okay. And we've just been starting each of our classes thinking a little bit about the ethical ramifications of technology, and because we are who we are here at Westmont, we often tie that into a biblical narrative of how technology impacts us. And we've specifically been looking at legal regulations, and we're going to build on that a little bit going forward, looking at legal regulations that fall short of what Christ calls us to, legal regulations that are more strict than what Christ asks us to stick with, and then legal regulations that permit things which actually are just straight up wrong, not just more strict. And to that third point, I want to point to one particular scripture that gives an example of that. Now, clearly in the Bible, Jesus doesn't talk about this with respect to computers, although a lot of the ways in which we work with technology ends up impacting the ways in which we also interact with legal regulations. And actually, evangelical Christians have kind of an obsession with legal regulations and how they end up regulating behavior and how they should and shouldn't be impacted. And we'll talk a little bit about that going forward in future classes. But here's one particular passage from Mark. It's a passage where Jesus is talking to Pharisees, which were religious leaders at the time, and he was addressing a legal regulation which he was calling out as being something which is wrong. And it takes a little unpacking here. For a better unpacking, I would point you to last Sunday's sermon at Free Methodist of Santa Barbara, where Pastor Colleen Hurley Bates did a great job of treating this in a deeper level. But for today, I'll just read it for us. For Moses said, "Honor your father and mother, and anyone who curses their father or mother is to be put to death." So Jesus establishing what the existing legal regulation was in the Old Testament. But you say that if anyone declares what might have been used to help your father or mother as Corban, meaning that is devoted to God, then you no longer let them do anything for their father or mother. Thus you nullify the word of God by your tradition that you have handed down. And you do many things like that. Snap. So what God is saying there is, or what Jesus is saying there, is that additional laws have been put in place that alleviate a person's requirement from taking care of their parents if they decide that the energy, help, money that they would have otherwise used to take care of their parents is this special category of Corban, at which point they're no longer required of taking care of their parents. And so this would be an example of a legal regulation that allows someone to do something which God considers wrong. So basically abdicating their responsibility for taking care of their family, and a legal remedy for doing that, which is actually contradicting what Jesus points out as Old Testament law. So a lot of details in this, a lot of background about what the building on top of regulations that were in place. But the bottom line is that this is an example of a legal regulation that permits that which is wrong. Christ is calling out the people who made those and telling them that it's wrong. There are examples of that in technology all the time. We talked about pornography being an example of that. That is something that is legal as part of free speech. I think it's a pretty easy case to make that that is something that isn't in conformity with what Christ would call us to. So technological regulations may permit things that are wrong. So we'll continue to look at some of these things going forward. Okay, so for today's class at the weeds, we're talking about the legal regulations at this high level, but we're also working way down at the low level in loops and if statements that eventually build up to these things, right, and change society. So administratively for our class, we've got a quiz on Chapter 3 due tomorrow. Programming assignment on Chapter 3 is due tomorrow as well, and I think I saw a few people had handed them in already. That's great. No need to procrastinate. Quiz on Chapter 5 is due Monday. We're going to be working through Chapter 5 and we're working through Chapter 6 today, trying to get to Chapter 15. And we'll have another programming assignment up shortly. I'm still working through which one that's going to be. Questions administratively? Okay. Anyone online? Questions? Okay. Then, where we were last time is we were working through some of the details of if statements, and generally they are decision making within computation. So we have these examples of if statements. We looked at them in this idea of a flow chart. Some people are able to understand how these if statements work if they kind of have this visual language for it, the flow charts. But at the end of the day, we've got to translate that visual flow chart into kind of a linear sequence of text. And so you have to understand how that linear sequence of text relates to the control flow. So we looked at relational operators, things like less than, greater than equal, double equals. We looked at the challenges of comparing floating point numbers because floating point numbers don't have exact precision. We looked at what it means to compare object references, and by that we dug into what the difference was between double equals, meaning checking whether the memory is literally the same, equals, checking whether or not those references should be considered the same. Two rectangles, should they be considered the same even if it's not the same memory? And then we looked at the compare to method, which is a little bit, it's a building on the idea of the equals operator, but instead of just telling us whether something's equal or not, it also tells us how they should be ordered, which one should come before another one. In class, we explored the lexicographic ordering of strings and worked through some of the rules of that. And then we ended last lectures talking about how you can test whether an object reference is null just by saying equals equals null, if equals null, if a reference equals null. And then finally, we introduced the Boolean type, which is either true or false, and that's how a condition gets evaluated. And we introduced two relational operators, the double ampersand for and the double vertical bar for or, which enable you to take a true and a false from either side of those and evaluate them based on the rules of and or. So just to reiterate, and both sides have to be true, or only one side has to be true in order for that entire expression to evaluate to true. So today what we're going to do is we're going to start off by working through the code trace example that we didn't have time to do last time. And actually today we are going to, I'll put this on the slides. We're going to do this twice. This first one we're going to go through together. And then the second one, we have an example in Canvas to work through. So the second one, we're going to take a break and give people who are following along in real time the ability to work through it in Canvas. And if you're watching later, then you can do it later. This first example is designed to try and walk through what lines of code get evaluated for these inputs. And so what I'll do is I will walk through the first one, and then maybe we can walk through the other ones together. Okay, so we've got some code on the left, and these are if and else if statements. It's a chain of if statements and three different conditionals and a default at the end. And the first line where we say int hour equals in.nextInt, that's the syntax for allowing someone to type in an input from the console. So the right side, in.nextInt, if you've initialized in correctly, actually in has to be initialized, will read in an integer and assign hour to be that integer. So if we type in 11, the question is what lines of this code are going to get executed? So we're going to just go through line by line. And so at 11, we're going to hit line 1. And so line 1 is going to get executed. Hour is equal to 11. So 11 is less than 18. So we're going to run line 2. Time will be set equal to afternoon. And then we'll be done because we've hit one true statement in that sequence of if statements. And so we immediately leave and go past line 9, go to line 10. So the answer to question A, which lines get evaluated, is 1 and 2. Now, if you look at the intention of the code, you can see that there's something broken here. Because if what we're doing is inputting the hour of the day, and we've inputted 11, and what we've gotten out from that code is that time equals afternoon, we can see that it's broken because 11 in the morning is rarely considered afternoon. So, okay, Joy, you want to walk us through what about B? What if hour gets assigned 15? Yeah, that's good. So I guess the question's a little misleading. What is the output? There's actually not really any output here, right? It's just what does time get set to. So line 1 gets run. You said that evaluates to true. That's right. Line 2 gets run. Time gets equal to afternoon. That makes more sense. If you use 24-hour time, 15 would be 3 o'clock in the afternoon. And then we leave. And so we only run line 1 and 2. Lisa, you want to do C force? Right. So that's a correct interpretation of the code. Run line 1 and run line 2, and also correct, indicating that the understanding that there's a logic error in this code. We don't appreciate what it's doing because it's broken. So then I'll do line number 23. In 23, it's the first example that we see here where we reach line 1, we run line 1 because we have to check whether 23 is less than 18. That's false, so we skip it. So we skip 2. So we run line 1. We now run line 3. We say if hour is less than 12. It's not. So we've run 1, we run 3, now we go to 5. Is hour less than 6? No. So we've run 1 and 3 and 5. Now we run 7. 7 catches everything, and we've gotten here, so we're going to execute it. And we drop into that else statement, which is the default block. And in line 8, we say time equals evening. So at the end of that, time equals evening. That one kind of worked okay, but overall, it wasn't a very good piece of code. This is a great example of a piece of code that would benefit from having some JUnit testing. Because what you would do in the JUnit testing is you would say, well, if the input is 11, I want it to be morning. And if the input is 15, I want it to be afternoon. And if one of those doesn't end up happening, you would catch it in your JUnit tests. Okay, so this next one, the code's been written a little bit better. And we have it. This example is in our Canvas. And at the same time, so in Canvas we'll have this one, and then we have another example. Let's see, how should we do this? Because there's actually 2 examples I want to do. What we'll do is we'll just give some time to do this one in Canvas. The final question in our evaluation is on the next slide, so we'll just pause, come back, and then won't turn in the Canvas slide yet. Okay, so right off the bat, we're going to take a break. It's a break to work on this. So it's 10:38. We'll come back in 5 minutes, so we'll call that 10:44. And while we're gone, you can work through these inputs in the same way that we did the previous slide. For those participating in the class, there's a place in Canvas where you can enter the results. I'm saying it over and over again. So, okay, back in 5 minutes. Okay, we're back, and we just worked through that, and you probably noticed that this is a little bit better code. It's sort of questionable whether you think 5 in the morning is night or not, but if you accept that everything between midnight and 6 is night, then this code is set up much better. You can see the ordering between those if statements is logically progressing so that it catches the right things and you get the right assignments. And all we did between this code and the previous code was just reordering the if statements. So this is just to drive home the point that the ordering of those if statements makes a big difference in the correctness of the code. So the last one that to take a look at in that evaluation, oops, that's the wrong one, is this is a code trace example. So what I would like to do here is I would like to, in class here, what we're going to do is we're going to work together to try and write this code. And then for those going on at home, you can just work straight into the Canvas example. We'll take our answer here and put it into Canvas when we work together. Just to set up this question again, we're assuming that we're starting at Westmont, which is in the upper right in the red circle. And this is maybe something like a robotic Uber car, self-driving Uber car. And what we want to do is we want to be able to answer the question, where are we, in terms of which of those 6 or those 5 sort of greenish circles are the destinations. Each one of them is a park. And we would like to be able to output which park we're at just by looking at 4 different Boolean variables, right at A, right at B, right at C, and right at D. Now the car doesn't know where it is, but it can evaluate. It does have the correct answer for those 4 variables, assuming that it started at Westmont. So for example, if it went left at A, it would be at Hale Park. And so the job of this assignment is to come up with an if-else statement that takes those Boolean inputs and returns the correct park that you're at. Does that make sense? Okay, so here in class, I'm going to have us work together on the board on it, and then at home you can do it however makes sense, and put the answer into Canvas for participation today. We'll take maybe 6 minutes to do this. Come back at 52. Okay, we're coming back in, and we had a good discussion here about how to go about solving this. What the right answer is depends a little bit on the structure that you're putting this in. I was imagining that you would return a string that was the right answer, and so if you had something like that, you might get a certain kind of answer that's a little bit different. Let me just give a little hint for how you might do the first one by dropping into code here. Reveal. Wizard of Oz is revealed. Okay. Let's just make a new, put some space here. We're going to look at this in a second. Let me just make a new class where I can put some code that we can look at. A little bigger. So what I was imagining is something like a function that would be public string where am I, and it would take in the Boolean right at A. Set it up for us. All right, so that's the structure that I was imagining for the code. And so you might say for the first example, if not right at A, then you would do something like return, what was our first park? Hale Park. And that would immediately never want to get to that end, but I just did that to get rid of our errors. So that would immediately stop the execution of the control flow as we hit not right at A. But if we did go right at A, so if right of A is true, we could either put the code below here, or we could put all the rest of the code in an else. Either of those would be equivalent because we were returning in the true statement. Other ways in which we could have written this if statement up here could have been if right at A equals false. That would have been okay too. It's a little redundant. That's all right. And we could have also said if right at A is not equal to true, which is also a little doubly redundant, but that would be all right as well. So a couple options. So this is just part of the solution. The rest of the solution would follow from this, and I'll let you guys work through that on your own. Okay, so that is kind of a summary of what we're going to, that was the if statements, that was if-else statements. That's basically what we want to know when it comes down to the decision making. We're going to use that, of course, going forward, but that gives us a structure to start from. What we also need to do now is we need to talk about looping. Looping is like repeated if statements, and there's a few more looping constructs in Java, but there's three basic ones that we use: the while loop, the for loop, and the do loop. And each of these have slightly different structures, but they're largely equivalent. They have a lot of the same capability. They're different syntax for doing the three different loops. And first thing to start with is, why do we care about loops? Well, one of the things that computers are really great at is doing repetitive calculations over and over and over again quickly. And loops allow us to repeat things over and over again very quickly. And by cleverly using loops, we can get a lot of work done. So if we need to repeat a particular part of our program over and over again until a particular goal is reached, a loop is what we want. Maybe that goal is to run some code a certain number of times where we know the number of times beforehand. Like maybe we want to add up the first 100 numbers, 1 plus 2 plus 3. So we would know we need to do that loop 100 times. Maybe we want to run until a variable reaches a certain value. So maybe we want to continue running until something that we don't know the answer for, but we know the threshold is reached. And maybe we want to keep running loops until all the data is processed, but we don't necessarily know how much data there is. Or maybe we want to run a calculation that requires repeated steps, like calculating the average of a bunch of numbers. All those things would leverage loops along the way. So here's an example problem we can look at. This example problem is an investment problem, and it is one that is common. in this case, we'll structure it as you put $1,000 into a bank account, and we'll say that that bank account earns 5% interest per year, much higher than most bank accounts now offer, but at some point in the future, it'll probably be up at that rate again. The question is, if we had a 5% interest rate, how many years would it take for that account balance to be double the original investment? How long are you going to have to wait until the compounded interest doubles your $1,000 to $2,000? Well, this is a loop. We don't know how many times, but what we can do is we can simulate that interest-bearing account until it gets to the point at which we've doubled our interest. And so that would be a way of using our loop. So what does that look like? Well, we'll have first come up with an algorithm. So the algorithm is a bit like pseudocode. It's a strategy for solving this problem. And the strategy that we're going to use might go something like this. Imagine that we had a table, and we're going to start with a year value of 0 and a column for the interest and the balance. So we're almost setting this up like we're doing it in a spreadsheet. And what we'll do is we'll repeat each of the following as long as our balance is less than $2,000, which is what we're looking at, because that's double our balance. Now notice as long as the balance is less than $2,000, we'll do it. If it's greater than or equal, we've met our condition and we want to stop. But while our balance is less than $2,000, we'll add 1 to the year value. So this will be as if we've completed 1 year. We'll compute the interest on the balance from the first year, so 1,000 times 0.05, so that would be 5% interest. We'll add that interest to the balance, and we'll keep repeating that until we get over 2,000. And once we're greater than or equal to that 2,000, once we're greater than or equal to 2,000, we'll just report how many years we had to compound that interest for in order to get an answer. Sound okay? Pretty good? All right. So the first couple years are going to look something like this. Year 1, we will have earned $50, and so at the end of year 1, our balance will be $1,050. And year 2, we'll have earned $52.50 because our interest is being calculated based on our balance that has compounded. And so at the end of year 2, we're going to have $1,102.50, and we'll continue going until we reach 2,000. We don't actually know what that answer is quite yet. So how are we going to do that with a while loop? Or how are we going to repeat those steps while the balance is less than 2,000? Well, first we have to look at what the syntax is for while loops in general. So our syntax loop for while loops in general are a new reserved word while, and the structure looks exactly like an if statement. There is a condition, and that condition is a relational expression that evaluates to true or false, exactly like an if statement. And the statements are one or more statements, exactly like an if statement. So in a lot of ways, this is just like an if statement, except we run it more than once. We go back to the beginning before we leave the control. As long as that condition is true, we're going to run the statements that are inside that statement body. So also, just like an if statement. If you replace the while statement with an if, this should look really familiar. As long as that condition is true, though, we're going to keep running the statement body until that condition changes. So we have to structure our conditions in a particular way to make sure that it is possible to leave that loop. So here's an example of a solution to the interest problem that we just proposed. So we're going to assume that some of these variables are available to us. So we assume that we have a balance, which is keeping track of what we start with. So as we enter this loop, balance is going to be equal to 1,000. And as we enter this loop, target balance is going to be equal to 2,000. And so we can, if we read that like an if statement, we'd say if balance is less than the target balance, we're going to do this code. We drop into the code. We increment our year variable. So if it was 0, it's now going to be 1. And reflecting the fact that we've completed the first year, we're going to calculate the interest that we compounded from the first year. So it'll be the balance times our interest rate, which is, if it's 5, we'll divide by 100 to get 0.05. And so the interest, if we evaluate this statement, given that balance is 1,000 and rate is 5, will end up being $50. So in the third line, we increment our balance. We say, well, whatever our balance is now is what our balance was plus the interest. And now we're done with the statement body. If this had been an if statement, we would just leave the body and drop off the bottom and continue with the rest of the code. But because it's a while statement, when we reach the end of that curly bracket, we go back up and we evaluate the while condition again before we leave. Well, now we say, is balance less than target balance? It is. Our balance should be 1,050 now, and our target balance is 2,000. Well, balance is still less than our target balance, so we're going to run that statement body again. And as we run it again, year will be incremented another year. Interest will now be 5250. We'll add 5250 to our balance as it was currently updated, so 1050 plus 1050. 1050 plus 5250 ends up being $1,102.50. So after 2 years, our balance has been incremented. Balance is still less than target balance. But each time we go through this loop, our balance is growing. So we have pretty good confidence that at some point, balance will not be less than target balance. And the first time we go through that loop and balance is not less than target balance, we're going to leave that loop. And when we leave that loop, year will be set equal to the number of times the loop was executed, which also happens to be how many years we needed to accrue the balance that we were looking for. Okay? If we put this into a structure like a for loop, it looks just like the if statement. We ask if balance is less than the target balance. If it's false, then we just leave. We don't do the code there. If it's true, we run the code. Now, the difference here is what we do after we run that code. So in an if statement, we would go directly from here and proceed on. But the difference is in a while statement, instead of proceeding on, we go back up and we check the state, we check the condition again. We check it again and again and again and again, and we could run this loop forever, depending on what our condition is that we're checking before we leave our loop. At some point, though, we leave. The last time we check, notice the last time that we check, we don't run the code again. So the last time we check, we skip over the code and drop down. So that presents a little bit of an unusual pattern, because if you look at the code on the left, we'll check our while statement, we'll run our 3 lines of code, we'll check our while statement, and then maybe we'll run our 3 lines of code, or maybe we won't. The first thing that we do is we check our while statement, and the last thing we do is check our while statement. And in between, we'll run the statement body. It's interesting that we'll check our while statement one extra time over the number of times that you check your statement body, you run your statement body, because of the way the flow is structured over on the right. Not only that, but even if you never run the code in the middle, because in a while statement, just like an if statement, you might never run that true statement block. You might bypass it by going right on that false path the first time. And so you're always going to run the conditional check. You're maybe or maybe not going to run the statement body, depending on whether it evaluates to true or false. Okay, so our while loop syntax also enables us to declare variables inside our loop body. So these are considered local variables. So a couple of lectures ago, we talked about local variables and parameter variables. Inside the loop body is its own scope. And so we can declare variables within the scope of the body of a while statement or an if statement or any curly brackets. And that variable is going to be created each time we go into that statement body, and it's going to be destroyed before we run that statement body again. So we saw that as an example here. So let's walk through the syntax of what's happening here and just make sure we have a handle on all the different pieces that are present in a while loop. So the first thing is we've got our reserved word while, and we're in our conditional statement, our conditional expression, our relational expression here. We have some variables, and those variables had to be declared before the body of the loop. So somewhere above this code, we would have had to say double balance equals 0, or double balance equals 1,000. So it's not like these variables have to exist already. And they could be literals. They could be numbers or strings if we didn't want to use a variable. The next thing is that we have some kind of relational operator. We've looked at several of them, the less than, greater than, double ampersands. But whatever we've got, that entire expression has to evaluate to true or false. Notice there's no semicolon after the while. If we put a semicolon there, that would be the equivalent to saying there's no body to our while loop. We're just checking the condition and there's nothing to be done. So we don't put a semicolon there. Instead, we put the curly brackets. Everything in between are the statements that are executed while that condition is true. So we can have multiple statements. We can even have nested while loops. We can have if statements within that bracket. We can put whatever code is valid outside the brackets inside those brackets as well. And this is the example of a local variable. So this is a variable which is of type double, and it is an interest. It's called interest, and this variable is being created each time we go through the loop. When we're done with that loop, meaning after we're done running the balance equals balance plus interest line, that interest variable goes away. And that's important to remember, because if you think that it's retaining its value from iteration from loop iteration to loop iteration, that would be the wrong mental model. Each time you run that, each time you drop into that scope, that variable is recreated. Okay? So sometimes that's convenient, but sometimes you don't want that. For example, balance exists outside of this loop, and so only one variable, balance, ever exists as we go through this code. And the value of balance is being retained from iteration to iteration. So depending on whether you want the value to be retained from iteration to iteration, this helps you decide whether or not to declare the variable in the body of the while loop. Okay. All right, and then finally, just as a syntax note, the curly brackets are only necessary if your statement body is more than one statement. So if your body was only one statement, for example, it was year plus plus, you could just eliminate the curly brackets. If you don't have curly brackets, the assumption is that your statement body is just one line long. So you might see that if you're looking at other people's code. It's not very common that you're going to have a while loop with just one statement, though. The same thing is true about an if statement. I don't think we said that when we were talking about if statements, but if an if statement only has one line, that's part of its true condition, you don't have to put curly brackets. You can just have that one line. You didn't need the curly bracket when we were doing the write at A, write at B problem. You didn't need the curly brackets like you put on the board there, but it's not harmful. Like you can put it there if it's one statement. And especially when you're doing something in pseudocode kind of like that, it's helpful just to understand, what's going on. Plus, it's not, if you're writing pseudocode, it's not clear that by writing Hale Park is true, that when you would translate that into Java, it would end up being one line or multiple lines. So it's okay. I think that's fine. Okay, so let's hand trace this while loop. The ability to hand trace a loop is a very important skill to have, in that it helps you to make sure you understand the syntax of what's happening. It also is very important for the beginning case, if you never go into the loop, and the last iteration through the loop, to make sure you don't get off by one errors. And so I'm going to try and do this, but I need someone to help me out with the calculations, because we're going to have to update these calculations on the fly. So I'm going to try and draw it here in my kindergarten handwriting. All right, so we're going to start, and we're going to assume, I don't know if it's going to work. We'll give it a shot. We're going to assume that we start with a balance of 1,000, no lasers, 1,000. You probably have a calculator that'll just answer this right away. Great. All right, Joe, you're the numbers person. All right, 1,000, and we're looking for something that's greater than or equal to 2,000. And so we start with year 0, and so as we enter this loop, balance is less than target balance. 1,000 is less than our target balance, 2,000. So year is going to go from 0 to 1, and our interest is going to be 1,000 times 5%, which is $50. I happen to know that one. $50. That's a 5. Okay. We got to work on our handwriting. 150. Okay, and then our balance is going to end up being 1,050. All right, is 1,050 less than our target balance? It is. So now we're going to go through our loop again. So now year is going to end up being 2. Our interest, I know this one off the top of my head, is going to be 52.50. And our balance is going to be 110,250. Now I need Joy to help me out. Is 110,250 less than 2,000? It is, so we need to run our loop again. So now after running this loop, year gets assigned 3. All right, now I need help. What's 5% of 110,250? Yeah, what should we do? Let's round it up. So 13. Okay. So then what is 110,250 plus 5513? I could probably do that. Great. 1157.63 is less than our target balance, so we go to year 4. What's 5% of 1157.63? Great. If we add that to our balance, we get by that. Still less than our target, our goal. So year 5, 5% of 1215.51. 60.76. 1215.51 plus 60.78. 176.28. Help me out. 1276.29. That? Do we buy that? That looks good to me. Okay, so I mean, just one thing for like general life lessons to notice is that each year the amount of interest you're getting is going up. That should work to your advantage. All right, so year 6, 5% of 1276.29. Are we starting to love computers as we try and do this by hand and we see how long it's taking? Yeah, and our total ends up being okay. Let's just keep going. Yeah, 5% of this. So what are we looking at? It's going to end up being probably like 5 or 6 more iterations. 67.01. So then we're going to get 1407.71. Okay, actually I'm kind of satisfied. At some point, though, we're going to reach a balance that's going to be greater than 2,000. And when we leave the loop at that point, we'll look to see what our year variable is, and that's what we're going to output. Now, you just have to be careful about the logic of this, because if you start with 0, you just want to be clear that at the end of this loop, that reflects the state of the world after the end of year 1. And so when we get out of the loop the first time, this is what's true at the end of year 1. And so when we finally get out of the end of the loop, you have to be clear about what it is that your loop is currently representing. Great. Okay. I'm not sure there's much more to be said about that. But. Okay, so let's take a look at what this would look like if we actually went through and implemented it properly in Java. So I've got that standing by in an Eclipse program, and it's called investment.java, and you can see that what we've done here is we've created a class called investment. And so this is an object, and it's not exactly clear what this is trying to abstract, but basically the idea is to abstract the problem of solving how many years it's going to take to double our investment. So let's just walk through what we've got here. So it's in a project called while loop example, that's over here. It's in a package called investment, so that corresponds to this folder here. We've got some comments here telling us what it's doing. As we look at the class name, it's called investment. It's a public class, but it has private variables, one for the balance, one for the rate, and one for the year. We've got a constructor that takes in the balance and the rate at which we want to operate. And notice that the Java doc says that the rate should be passed in as a %. And then down here, we actually are dividing it by 100. So I'm going to clarify this and say, for example, 5% should be passed in as 5. Because if someone were to pass in 0.05, the units would be off, and just based on the way I've designed this. So that's an example of having to be clear in the parameter documentation what your units are. So we also initialize year to 0, so that's something that the user of our class doesn't have the ability to change. Basically, they're going to set up this class in order to do this calculation, and they're going to call a method called wait for balance, where they specify what the target balance they're looking for is, and that is the method that's going to run this calculation. Now, you can see that it doesn't have balance, year, or rate defined within the body of this method. That's because those are instance variables. And if we wanted to, we could have used the keyword this in order to clarify, oops, We could have used the keyword this in order to clarify that it is an instance variable. But because we don't have any local variables or any parameter variables that are also called balance, Java knows that we're talking about the instance variable in this case. Eventually, we're going to go through wait for balance, and we don't actually output anything, but year will have the correct setting when we're done. And so the final thing that we do when we ask is to get the year. So it's like we run the investment object, and then we ask for the result to come back. So this is just a class that executes this code. Save it. Sorry, this is just a class that provides the functionality. It doesn't run itself. So we have another class called investment runner that's going to go through and use that class. So investment runner is the application program, and investment, the class, is the systems program. So investment runner is using investment, just like the letter printer is using the letter class from our homework assignment number 3. So if we look at what we've got here, we've got a main function, and to match what we were doing in the slides, our initial balance will be equal to 1,000. Hey, side note, pro tip, in Java you're actually allowed to use an underscore for a comma, which is sort of a weird thing. I didn't know about that until I started teaching this class. Sometimes it makes it easier to read, except that you wish it was a comma, but you can't use a comma. So that means 1,000. Our interest rate is going to be 5%. You can see that what we're doing here is we're creating a new object where we pass in the initial balance of 1,000. We pass in the initial rate of 5 in the correct units that we specified. If we hover over this, we'll see the Java doc is actually being presented to us as the pop-up window. So that's another reason why it's helpful to use Java doc, because Eclipse knows to parse that Java doc and present it to you as the pop-up window. So look down under parameters where it says a rate, the interest rate percent, for example, 5% should be passed in as 5. That's what I just typed in, right? I just added that to the documentation, and now it shows up when I hover over the constructor, and that helps me just really quickly to see the documentation for it. Documentation, just-in-time documentation. So now I have this object that I'm working with, and I make the call to wait for balance. And what am I waiting for? Well, I'm waiting for 2 times the initial balance. That's actually going to run the loop, and then when this is done running the loop, it will return from this statement, and if I want to get the answer, I will get the answer, which is get years. And so I can save that, and I can run it. I'll go ahead and do coverage as a Java application, just so that we can see what gets executed. And down here in the console, we can see that it was going to take 15 years for us to answer that question. So I can't, I was going to run it just for 7. What did we end up getting for year 7? It was like 1,000, what was it? 1340, let's call it 1340. 1340.10? Okay, so let's just say we want it to be over 1340 even, and if we were to run that now, it would double after 6 years. Well, except it's not doubled. So this, okay, we just changed this, would be your target. After 6 years, so thinking through, did we make an error or are we just remembering wrong? Not sure.
Oh, I think you're asking for the number after the 7th year. Oh, that's the number like going into the 7th year, so.
I don't remember.
After the 7th year, it'd be 14.
Okay, so that seems to match up with what we calculated. So we just used the abstract idea of 2 times our initial balance in order to capture what the problem initially asked for. So it takes 2 years, it takes 15 years in order to double our initial balance. So now I'm going to step back and put on my dad hat. My dad hat says you should do this. You should invest money in a bank account that has compounded interest, and you should do it while you're young. Because how long does it take to triple your balance? Well, it took 15 years to get double our money, so is it going to take 30 years? No, 23 years. So wait, it took 15 years to get double our balance, but it only took an additional 8 years to get that same amount of money again? Wait, so how long does it take to get 4 times? 29 years. Wait, that additional chunk only took 6 years? It's dropping on us. Going from 29 to 33 is only 4 years. Each additional year that you add is going to take less and less time in order to what was originally your double. So it took 15 years to double our money, But how long does it take to get 10 times our money? 48 years. That's pretty good. I mean, it seems like a long horizon. No, it starts to grow really, really fast. And so this is also just if you start with an initial balance of 1,000 and never do anything else to it. If you were able to put in $1,000 a year and that's able to compound, you would get this incredible rate of return. In fact, I'm so into this. Let me show you a slide for it. All right, this is total. This is just me putting on my dad hat. So these are the bank accounts for a couple different people. So we've got blue is Chris, and we've got dotted line. Did I get that right? Let's see. So Susan is investing $5,000 between the ages of 25 and 35, and then she ends. So she starts on the blue line and then becomes the dotted gray line. And Bill is investing $5,000 annually between the ages of 35 and 65, and he's the green line. And then Chris continues to invest $5,000 from 25 until he's 65. And look at the difference between those initial 10 years. Susan invests $5,000 for 10 years. Chris invests $5,000 for 40 years and is never able to catch up with the amount of money that Susan gets in that gray dotted line in the middle. This is all just speaking to the benefits of starting early in savings, because Susan never had to invest any more money and was able to keep, retire at a higher level of income than Chris. So that's my shout out to dads everywhere. Okay, so that was Investment Runner. What we did with Investment Runner is we built an object that within it had that while loop, and we used that while loop in order to calculate the investment question that we were looking for. So let's next do an exercise where we try and do hand tracing on our own of a while loop. And then so in this example, it's not as clear what is happening. But what I'd like to do is it's 11:32, so this would be a good time to take a break and work on this. So what we'll do is we'll take 10 minutes, 5 minutes in order to work on the problem, and then 5 minutes to get some water or rest break, whatever we need. And so for part of that, practice running this code in hand tracing. Obviously, you could type it in, but it's important to be able to do it just by hand so you get a sense of being able to calculate this on your own. And the question is, what is going to be output to the console if we run this code? And so in this case, we actually have a system.out_print statement. And we will come back in 10 minutes at 11:43, and we will go over the answer to this. So see you soon. All right, we're coming back a little bit early, and that's because I am a liar. Our family has a funny, we have a kind of weird family culture, but you guys familiar with Little House on the Prairie? So there's this one episode where like Mary steals a book from the library or something and lies about it. By the end of the show, the barn is on fire and she's like trapped inside, and it's all because she lied about the library book. So in our family, we call that Mary's Web of Lies. And I am entrapped right now in Mary's Web of Lies because I said we'd be back at 43, and here it is, 39, and we're back. That's okay. We'll carry on. Okay, so when we were going through this here in the classroom, one thing that we were talking about is the ending condition and whether or not we actually ended up printing 256 or 512 as our last number. And the correct answer would be that 512 is the last thing that's printed out based on this code. You should have also recognized that all the numbers get printed out on the same line because we're using system.out.print, not system.out.println. And you would have to reorder the code if what your goal was to not have any numbers printed out that were greater than or equal to 300. And there are different ways that you could change the order of your code in order to achieve that, if that was your point. The easiest one would have been to reverse the order of the two lines that are in the statement body so that system.out.print came before n equals 2 times n. That would achieve the goal of not printing out any numbers that are greater than or equal to 300. You would just have to be careful because your starting condition would be slightly different. The first number you would print out in that case would be 2, not 4. It's worth pointing out that just like a while loop might never be run, for example, in this code, if n were equal to 301 or even 300 when we started, that while loop body would never get executed. It would be in our code, but because n, when we first got to that conditional statement, starts off at greater than 300 or equal to 300, we would never enter that code. So there's one thing about while loops is you might never run them. The other thing is you might run them forever, and you might never get out of them. And so we call that an infinite loop. That is a bug, usually, in your code. And so let me just point out what that looks like by going to Eclipse. Where's our Park code? This is just my place where I can put some code. Here's an example of an infinite loop. If we run this, we're going to see, actually, let's put it on one line so it's a little more dramatic. If we run this, we're going to see that our console fills up. That was less dramatic than I expected. Shoot. All right, so right now we're stuck in an infinite loop. If we come down here, this line is just going on forever and ever. And actually, it's going to really cause a problem with my computer here in a second. So if you ever find yourself in an infinite loop, running in Eclipse, the way you can get out of it is shifting to your debug perspective. Oh, I'm already getting into trouble. Selecting over here in your debug window the process that is running. I'm using up resources. Oh no! And hit the red stop button. That'll stop your program. It'll hard stop it. It'll just force quit it. If we had, I wanted that to wrap around, but the console didn't wrap around. So to just prove the point here. You can see that it's going on and on and on and on and on and on forever. Now, that's not shocking because we just have this statement while true there, right? That seems obvious, right? If you were to type in while true, well, you better expect that you would have an infinite loop. The real issue is that you often have infinite loops because you have conditions that you didn't expect. For example, if you had an integer n equal to 10 and you said, well, n is less than 11, you would also have an infinite loop. And now you're trapped in an infinite loop. And that's not quite as obvious that it's while true. But one of the ways that you can recognize that you are in danger of getting in an infinite loop is if none of the variables in your conditional statement change within the body of your loop. So one problem we see here is that in the body of my loop, n is never getting changed. And if n is never getting changed, then my conditional will never change. So either this loop is going to never run, or it's going to run an infinite number of times. If I have a situation like this, it's possible that I could get out of my infinite loop because n is changing each time in the body of the loop, and so my conditional has some hope of actually leaving the infinite loop. that case, we only ran it once because 10 became 11 and we quit. Just because we're changing something in our conditional, though, doesn't mean we are going to get out of our loop. So another thing I could have done is I could have said n equals n minus 1. And now we're back in our infinite loop. Because n, while changing, is not getting any closer to the completion. It's just going more and more negative, and n is still less than 11. Now it's minus 1 and minus 2 and minus 3. So infinite loops are not an uncommon situation. They're usually a result of logic that's faulty for some reason, and it's usually because you have some kind of complicated situation that you didn't expect. But one of the ways that you can check to see what's going on is you can put a breakpoint in, and then if you run your program in debug mode instead, Eclipse will shift you over to the debug mode, and you can look and see, okay, I'm stopped in line 10 here. I can look up and I can see what n it has a value of. I can step over each line of code and I can see, I see, my n is getting lower and lower. And so each time I hit line 9, my while statement is evaluating as true. And the reason I'm stuck in my infinite loop is maybe because I have a bug in this statement here, depending on what your intention is. Now as I step through my loop, I can see that n is growing. I get to while n equals 11, and I kick out of my loop. So debug, great, big friend. We love debug. Infinite loops caused by faulty logic in your while condition. It's not uncommon to run into them. It usually is a bug. Another thing that you run into are off by 1 errors. And off by 1 errors are, for example, in our investment runner, if we weren't careful about our years and the number of years that we were paying attention to. So we could very easily, in our investment runner case, have written our investment code so that we started with year equals 1. That doesn't seem unusual, but if we were to then come down in our investment runner and ask how long it would take to double our initial balance, make sure I'm running the right program, we would get 16 years. And 16 years would be 1 more than it should have been. And that's because we didn't hand trace our loop, and we didn't make sure that our intention was correct, and we weren't clear about what it is we meant by a year. And so you have to be careful both at what you start your variables at, 0 and 1, and you also have to be careful about right here, this, someone's trying to join me. Hello, everyone. You also have to be careful about this conditional statement here. You can get off by 1 errors by not being careful about your less than versus less than or equal. So that can give you a slightly wrong answer as well. And it all depends on exactly what it is you're trying to calculate, and that is a big reason why ham tracing is valuable. All right, so let's do an example of hand tracing code. We've got a couple of them. This is an example of a while loop that is doing something. And so the question is, what is this code doing? And the first thing to do is to just trace through this code to try and manually understand what's happening. And then once we manually understand what's happening, to step back and take a look at what semantically it's doing along the way. All right, so let's take 5 minutes, and locally here we can do it on the board, or if you're at home you can do it on paper, and we'll come back together and talk about what it's actually doing. Okay, back in 5. Okay, so we're done doing this in-house, and what we got, the team here in the studio audience got as an output was 2. That looked like the right answer, and we were talking through what the intention of this code was, and we recognized that the intention of this code was to count the number of digits in our initial integer n, how many of those digits were 6 or 7. The mechanism that the code was using to do that was it was pulling off the digits one at a time from the bottom. It was doing that by doing the n modulo 10. That would pull off the lowest digit, evaluate it, and then the next body through the loop, it would remove that lowest digit by doing n integer division 10. So a couple things that usually trip us up is not knowing what the modulo symbol does. So that's something to learn if you don't know what it is. The modulo symbol looks like a percentage sign. Another thing that sometimes trips people up is not understanding how to evaluate the double vertical lines, the Boolean OR statement, and then not recognizing that n equals n divided by 10 is doing an integer division, which is not rounding. It is dividing a number by 10 and then throwing away the fractional part, regardless of whether it's greater than 0.5. So an integer division, integer modulo, sometimes making sure that you're carefully taking care of the last iteration through the loop. Sometimes people mess up the last iteration on the loop. But that didn't happen here today. So the only thing that we did in terms of the skill of hand tracing was being really careful about writing down each of our digits through each iteration of the loop, and just being a little bit OCD about that so that we make sure that we didn't lose track of where we were in the loop or get ahead of ourselves logically. All right. What does that code do? It counts numbers of 6s and 7s in our initial number. All right, let's do one more trace. We'll do 2 more, and then I think we'll call it a day for today. So next question is, what does this code output? And we'll take a second to evaluate that. Online, stand by. Okay, audio is online because I put this slide a little bit too soon. This slide doesn't actually have a while loop. It has a for loop, and we haven't introduced a for loop yet. So being able to trace this code would rely on background knowledge that we hadn't actually introduced yet. So alas, we can't do this one yet. We'll do this one next time. Okay, and so that puts us at the end of our slide deck for today. Let's just review what it is that we were talking about today. Today we finished up our if statements. So we had if and else statements. We worked through some conditionals. We looked at how the ordering of those conditionals mattered. We tried to write some conditionals in order to pretend like we were a self-driving car. And some of the things that we had to iron out in that process is we had to iron out how the return statements worked, how the structure of what it is how this is embedded in a greater body of code matters exactly how the if statements come together. Then we introduced the while loop. The while loop is just like an if statement, except that it executes the body multiple times based on a condition, and those conditions rely on the same relational operators that we have in if statements. A couple things that can happen though in while loops is we can get infinite loops, and we can get off by 1 error, so we have to be very careful about the ways in which we look in particular at our starting conditions and our ending conditions. The next thing that we're going to tackle is we're going to tackle the for loop, which in my mind, the for loop is just a while loop that has some convenient syntax for us. And then from our while loop, we're going to leave the basic structures of Java, and we're going to start working into data structures and start thinking about, okay, great, we know some basic ways of making decisions and loops. Now let's see how can we make some more sophisticated data structures to hold the kinds of information that we might be interested in working in. So after we're done looking at those loops, we're going to kind of take a step up and look at a little bit more sophisticated understandings of what we're doing with data. All right? Any questions? We're good? Anything online? All right. That's it for today. See you tomorrow.